to have Ivan Losev tell us more about quantum categories, and he has to do even better than yesterday, which is probably impossible from what I've heard, so no pressure.
All right. Thanks for coming back. So, the topic for today is the affine Hecke category. So let's try to start with a little recap. So last time we have introduced the category that we call quantum category O, also by all epsilon x. So epsilon here is the primitive D is root of unity, and D is odd. And the fact that I stated about this category is that it decomposes into the sum of blocks. The sum is over objects they call theta, and I'll recall what this. Blocks called O epsilon theta. And the theta here is so the chance over orbits of the affine well group acting on the root vectors. So lambda 0 is affine well group. And lambda 0 is the root vector. I haven't given any indications of proofs, but apparently the notes are going to be posted, and in the notes there is some stated proof of this fact. So what does this decomposition tell us? It kind of tells us that at least some aspects of this quantum category O are controlled by the affine well. And in fact, this connection goes much further. Somehow, the goal for this lecture and in a different version for the next one is to relate all epsilon thetas to certain standard categories associated to this W of phi. And the standard categories are singular blocks, so generally singular blocks of the so-called affine Hecke category. So in a sentence, the affine Hecke category is a categorical counterpart of the affine Hecke algebra that Tom introduced in his talk yesterday. And an important thing to know about this category is that it needs 3 realizations. And I will work with the most elementary one in terms of topic type. The other 2 are constructible geometric, very similar to what appeared in Tom's talk, and then coherent geometry. Those, however, I will not mention. Okay. So let's start with a definition / construction. For the time being, I'm going to work with so-called regular. So the general setup is the following. I will have W prime. This is the reflection group. And it acts on its reflection representation, for V. So the most important example for us is when W prime will be affine. And V is a fine quantum that I'm going to think about as the sum of the finite quantum, German H, plus one-dimensional space with basis element H bar. And so the action is as follows. So H bar is invariant on this action. Then I need to tell you how what happens when I apply the an element from here to an element of H. So for the finite part, acts on H as usual, and by this I mean the usual linear action. Now, if I have an element from the lattice, lambda, then the corresponding element T sub lambda in the affine while group acts on X by X plus lambda paired with X times H dot. For all X in the curve. Okay. That's an action of the while group of affine Cosmology algebra on its curve. Okay. A couple more notations. Let me have a notation for the set of simple reflections. Equal S. And R is going to denote the symmetric algebra of the graded algebra coming with an action double. And Wolfgang Zurgel told us to care about certain modules and bimodules over this algebra. And here is the most basic bimodule that we are going to care about. I fix small s and s capital. And from here, I can consider, I need to write it in full. I need to write both Samuelson. So both Samuelson bimodule. I'm going to denote B sub s. You know, basic rule for the talk is not to write ds on the board. So by definition, it's the following: it's R tensor with R over R super S. So this R super S is just a subalgebra of S invariant. Okay. R is a pre-ranked module over this R sub S. All elements F R. So I got a bimodule, and notice that it comes with an initial grade. As long as it's a bimodule, it's naturally graded. Are there questions? Yep.
Are you not going to shift the grading by one?
Very soon we will all forget. You can shift it, but then we'll forget.
You had capital S and B is the symmetric algebra?
Yeah.
Okay. So distinct from this set has simple reflection.
Yeah. You know, there are as many letters in English alphabet.
Sure, sure.
We make the right thing. Okay. Now I want to consider certain subcategories in categories of modules and bimodules. And those ambient categories are going to be denoted by R group by mod and R group mod. the heads categories graded are modules and bimodules. They care about certain additive subcategories. Disobedient additive, well, full subcategories. So first, we're going to care about the full subcategory that I will denote by SB. And this is what usually called sorted by. Sorted has some other name for this, which I already forgot.
Special bimodules?
Special by, that's right. So who are those? So these are objects. Well, it's a full subcategory, so morphisms here are going to be all morphisms of graded bimodules. I just need to tell you who the objects are. So objects are obtained from the regular bimodule R, and also this both Samuelsons with a less, via the following operation. So what can I do with bimodules? First, I can take direct sums. I can take tensor products over R. Tensor two graded bimodules and actually get a graded bimodule. Then I have gradient sheets. If I have a graded bimodule, I can just preserve the bimodule structure but shift grading by some. And then finally, an operation which looks innocent but actually is the most non-trivial of them all, I'm allowed to take direct sums. Yeah. They actually find it. And so, what do I do? So I take some number of the both Samuelsons, maybe a zero number, I tensor them all together, I get a gradient bimodule. I can take, I can treat the grading how I want, I take primary direct sum, and then take direct sum on C. And this is sort of that. Then there is a category of sorted modules. You can define similarly, but I'm going to define it a bit differently. These are now graded R modules. And these are modules of the form B, mod BV. So B is where B is a sorted bimodule. Okay. So I'm taking the sorted bimodule and then I mod out the action of the variables on the right side. We can say that I tensor over R with a one-dimensional gradient model. And the fact of life is that this flows when taken direct sums, which is not obvious. Okay. Finally, and kind of most importantly for the purposes of this talk, I want a certain variant of this S mod, which I'm going to denote by S mod underline. And I call this ungraded sorted bimodule. models. Graded sorted models. So what do I mean by this? Is that objects in this category are the same as in S mod, but I forgot the grading. Meaning that the morphisms now are all linear maps. So before in this S mod, morphisms are graded linear maps. Linear maps preserving the grading. Now I just want to consider all linear. Questions?
In S mod, do we distinguish between formal grading shifts of the same underlying bimodule?
Yes.
The same underlying module. Do we do the same in S mod underlying?
No.
Okay. So the objects are.
So objects are not graded. You can formally degrade the category. So you can say that if you have two objects here, you consider all forms from object number 1 to gradient shifts of object number 2, and you sum them all together.
So, is it fair to say that the objects of S mod are the same as the object of S mod underline or the objects of S mod up to grading shift?
You can, but the different gradient shifts are now deep to know. All right. Now, an important thing about all these categories as beam, as mod, and as mod underline is that they are so-called Krull-Schmidt. Meaning that every object in these of these categories is isomorphic to the unique direct sum of intercomposable. Meaning objects that cannot be decomposed into direct sum. Okay? And then you can ask, well, how do I classify indecomposable objects? And there are answers for all these categories, which are part of so-called sorting categorification theorem. So, proposition, example Sorgel, due to Sorgel, which I'm going to state for S mod under. It says that indecomposable objects in S mod underline are in a natural bijection with the elements of the group I studied. So before I move on, so let me just explain where is the affine Hecke algebra sitting. Notice that SB is a monoidal category. It's a monoidal identity category. You can take the so-called split K0, where you identify the sum of two objects with their direct sum. This is going to be an algebra, and you can ask what algebra do you get. The answer is the correct. What other? Okay. So now let's get back to kind of the purposes of our lectures, and I promise you some connection between this affine Hecke category and quantum category also. Let me try to state the most basic version. The categories I consider are additive categories. And so what I want to do, I want to convert them into triangulated categories. The most basic way to do it is just to take bounded homotopy. So let me introduce notation. Here H for Hecke going to be KB as mod underline. And this KB here will just bound some of components. That's a triangulated category. And let me state the first result, which would be a derived equivalence, more precisely, equivalence of triangulated categories. In the case of regular. And it's a theorem due to myself last year, which says that if theta, so theta was an orbit of W super A, so if theta is free, so such a block of category O we call the regular block. So if theta is free, then dB of O epsilon theta is equivalent to the triangulated category to the same. So the level of triangulated category is also the same.
Theta and orbit on V or on
It's orbit on lambda 0, which lives in the dual.
How does epsilon appear on the right side?
Doesn't. It essentially doesn't. I'll make a
Do you allow D equals 1? Do you allow D equals 1?
Do I allow D to no.
No.
How negative one? Let's play a game. Everybody writes a paper.
Well, 3.
Piece of paper and just keeps this piece of paper to themselves. I think it should be fun.
it has to be bigger than maximum.
Wait. Look at it. So I should say that a weaker version of this with some additional restrictions on D due to Chan C2. Now a remark, for a free orbit to exist, one needs indeed the D is bigger than the Corsican. Let's say the Corsican number. Say if G is a SLM, then H is equal to A. So if this condition is violated, there are no free orbits. Otherwise, there is. If D is bigger than H, then the following orbit is free. I can just arc by W A on the element 0. It will give me a free orbit. And the corresponding block is called principal. There are questions?
Yeah. So how is the WA action? How does that know about WB?
So the action here has translations to scale by.
Is there some kind of compatibility with the result of arXiv as a Ginsburg? Like where if you forget the affine Grassmannian should be Wahori or something, that corresponds to a subcategory?
It should.
Okay.
Has an I don't think this has been proved, but this is widely expected. Okay, so this theorem concerns regular blocks, but not all blocks are regular. I need to explain what happens in general. And for this, I need a little bit of combinatorics.
Sorry, on the left, can you recover the graded version for O epsilon, the principal block, please?
So the categories defines representations related categories usually don't have this kind of easy to see grade. If you wish, there is a coherent realization of this, which is easily gradable. Yes, you can have here a mod, and you can have here. All right. So now let's take theta, not necessarily free. And I want to explain generalization of the theorem. For this, I need a bit of preparation. Let me define the following subset of lambda 0, the root lattice, and this is A for alpha. My A is going to be the following. It's all lambda and lambda 0 subject to the following inequalities. So lambda plus rho squared is alpha I check is less or equal than 0. Okay. And lambda plus rho squared is delta check. Delta check here is maximum forward. Is big or equal than minus. Okay. So that's kind of anti-dominant of. And a little exercise is that this theory A is a fundamental domain. For W super A epsilon lambda. So now, what does it mean to be a fundamental domain? It means that every orbit intersects the set at a single point. Let me take the point of intersection of my orbit theta with it. Let me call it lambda super 0. So it's a unique point. In A intersect with theta. Okay. And now this defines for me a subset in the set of simple reflections. So I will be taking simple reflections, I ask, just reflections about the walls. Okay. So just notice that kind of it's not quite compatible with, I mean, it's not quite the same what's written here. So rather, this is actually on the affine carton, and my lambda 0 embeds into the dual affine. So reflections about walls of A, and let me define a subset J. It's all reflections in S, such that S dot lambda 0 is equal to lambda 0. Of course, if my orbit is free, then my lambda 0 lies inside of the interior of this alpha, doesn't lie anymore, and the subset is empty. Otherwise, it's a It's gives you a Lincoln diagram, it's fine. Other questions?
How can 0 be 3?
No, everything is row shifted.
I have a question.
Mhm.
Is there a way to think of this thinking diagram and just have that as like the thinking diagram for some centralizer of this element?
In a group, yes.
Even with this shifted action, what is that changing?
We just need to properly shift where. In representation theory, it's, you know, when you look at categories O, your action is usually shifted. And so what you do, you kind of consider an element like exponential of 2 pi I lambda plus rho in your torus and things.
Okay.
Yeah, I see you wrote that.
All right. So now the last piece of notation. Well, my J gives me W sub J. That's W of fine. It's now a finite reflection. And then I can take its invariance, which I'm going to denote by R super J. Just invariance of Wj inside of R. And it's a finite reflection group, so what I get is algebra of polynomials. Polynomial. All right, so it was kind of a lot of notation, but now I'm able to state construction, and there's going to be a singular block in my category, and after that I will immediately be able to state generalization of the previous. So definition. That's going to be a J singular block. Fine. Correct? So let me maybe write a trivial thing. This ring of invariance sits inside of R. That way, if I have a module over R, I of course can view it as a module over the subring. Okay. And so I define the category as not underlined with subscript J on the left. B, it's a full subcategory in the category of modules over R super J, whose objects are direct summands of objects in S not under. Viewed as modules over this smaller. Okay. So I take my graded sorting module, I restrict an action, get some module over J. Even if my initial module wasn't decomposable over R, this new module very well may be decomposable. And take all possible direct sums. I get this pattern. And since, so that's still an empty category, I can convert it into a triangulated one, and that's going to be category which has the node H with superscript J on the left, is just KB. Of my edit. That's some kind of category of singular sort. And you can guess what the theorem is going to say. Says that dB of O epsilon theta is equivalent to this category H subject. And triangulated category. Of course, you can ask what happens with abelian categories. I'm going to repeat the version of this question: what happens with G structures? So you can ask what happens with plane structures. And to some extent, this is going to be addressed in the last lecture. Last lecture tomorrow is the best time possible for a lecture 8:30 a.m. Sunday. All right. Other questions?
Seems like to get this category, the right category, you're actually forgetting some grading structure. So if you remember it, you have something extra on the direct, I mean, on the operational problem.
Yeah, I obtain a grading on this category. I need to be a bit careful with
The direct.
these structures. Fact. Gets it. You can do it. It gets a little bit technical.
But it's there.
Yeah, it's not written.
No. I mean, it's some extra structure that is present.
Yeah. All right. So, in the remaining, I don't know, 10 minutes, I'm going to tell you something about why one could care about having such a signal. That's the last part for today, and it's about motivation. So last time I had three forms of quantum groups. There was the Concini cuts, there was Lustig, and there was this mixed. And people cared about kind of the Concini cuts and Lustig for a long time. Mixed, not so much. The mixed one was popularized by a guy called Dennis Gaidgori in this part of the world. Dennis Gaidgori, where he's from. So what he wanted around, I don't know, 2018, he wanted an extension of the famous Kazdan-Lustig equivalence. So what is this equivalence between? It's between some representations of the affine algebra and some representations of a quantum. So on the affine the algebra side, you have arc integrable G hat modules. That's a group which appeared in Tom's talk yesterday, and that appeared in Sasha's talk today. And this would be equivalent to the finite dimensional reps of Q epsilon Lustig, where epsilon comes as follows. For representations here, you can consider the level of the central element X. and you read epsilon from the left. Now, what Gainsborough wanted, he wanted to replace the group of arcs by evaporating. To get always category O. And then he argued that U epsilon L should be replaced with U epsilon mix. And then category. Things get more complicated. For example, here, if your level is negative, you get equivalence of abelian categories. This equivalence is never an equivalence of abelian categories. Gainsborough had some predictions with what happens to the T structures. And in fact, his conjecture which is essentially a theorem due to two of his students, Chiang and Hu. Basically implies the theorem, what we call it theorem prime, implies theorem. The method is very different though, and more fancy as you can imagine by the kind. It has some different set of restrictions on the root. And motivation, of course, comes from Langland's program. In this case, it's quantum. So that's the first part of motivation to look into the things.
Yes, sorry. Is there the continued class version on the client side?
Whereas people wanted to say things along the lines, you take restricted representations of the Concini cards and relate them to modules of vertex algebras, something affine W algebras associated with elements. I'm not sure what was taken. So this was kind of this is going to go back to Gainsborough. Let me tell you two motivations of my own. One, motivation number two, which is the hope that theorem prime plus its abelian version, of which I will say something tomorrow. To give rise to character formulas for certain, let me put it in quotation marks, but equivalent irreducible modules over the continuous class form, let's say with unipotent center, with unipotent Frobenius. Take whatever Frobenius curve type. So what the hell is written here? This algebra is like behaves similarly to the universal enveloping algebra of the algebra in positive characteristic. In particular, it has so-called big Frobenius center. It looks like functions of the graph on the open graph. And so we can specialize an element of the center and mod out from this algebra with something finite dimensional. And you can ask about irreducible modules over this finite dimensional algebra, which mostly are quite mysterious. Now, what is equivalently reduced? Well, then, this is subtle and hasn't been worked out. The motivation for this question comes from my paper with Rukavnikov from 2020, where we started a similar category for classical model for semi-simple algebras in positive characteristics. It turns out that if you impose a little equivariance on your modules, you can write like Kazan-Lustig type parameter. One can speculate that the same can be done in the quantum case, and actually this theorem can be used, this theorem prime can be used. That's motivation number two. This hasn't been done. Motivation number three is called caps. So my presentation doesn't really make it clear, but you should think about this category as a cute little kid. Okay? As many cute little kids, it has a big, old, angry, brother. Namely, what I can do, I can consider our epsilon mix. So before what I did, I took a simple algebra. Now I can put a hat on it. And I will have a fine quantum group where I specialize Q to root of unity. This is a very mysterious category from several respects, which we hope to defeat one day, continuing that analogy. But secondly, if one wants to understand this, one first needs to get some good understanding of the finite. All right, and with this, let me finish.
Any questions?
So in your three, what's on the right hand side?
Nothing so far.
Using like a double affine.
Yeah.
Something like double affine Hecke category, which is not yet exists. Well, at least the versions that exist are difficult to understand. So all these versions, as big and angry as this is, it may be the well, I mean, this one and its classical model one, what may be the
H sub j have like an explicit presentation?
It's like I was confused the two. It's either anti-spherical or spherical.
That's algebra? I mean,
It's not an algebra, it's a module of this.
And I have a question about this here. So I can see how the mixed quantum groups should be related to the Iwahori. And so in the same direction, the DK thing seems like it should be related to something deeper than the equilibrium. Something like, so we can do something in when we stop and talk about deeper level subgroups, you can take two alcoves that are next to each other. You can take the Bruat-Titz group scheme that is corresponding to this, that fixes both of them. And this looks like in the matrices, like, you know, sort of like putting in, it's like in the Iwahori, there's like slightly deep, there's like P on one side of the matrix, but not on the other. Put P on both sides. It becomes a slightly deeper subgroup. And I'm wondering if there's a geometric Langland's approach to this level structure that could shed some light on the decay.
So, some people thought about, you know, you kind of, I think an expectation is that you look at deeper level structures and you get reasonable categories, there's still like that. There's a work of Jiang Chao Xia, who's a graduate student of Zhou, book results along those lines. And so I think what you do, if you want the continuity class, especially the Frobenius central production, you try to look at something like that. I'm not sure whether going to get access to geometric. I don't know.
Other questions? Okay, let's thank our speaker again. So maybe grab a bite. You have to be at 2 places at the same time next. So shore up your energy.
I'll contribute remarks. I'm dividing into 2 rooms. 108 is right across from all. Please move online and see which response you would like.
Same time. Oh, that was a good one.